Welcome, my dear JEE 26 warriors. Time to start our second class of electromagnetic induction. In the first session, we have seen what is Faraday's law and the three major variations of changing area or changing the field or changing the orientation and how it changes the flux and creates and induces electricity. And the second one, the Lenz's law, which gives me the direction. This is what we have seen in the first class. Today, we're going to see the concept of motional EMF, eddy currents, and induced fields. Although the major focus will be on the motional EMF part, these two are some, interesting things, some small topics which we need to, go through it. It's very small and it will not take much time, right? So let's begin with the class. Hi Ibu, hi Paya, hi Maha. Welcome 3 in 1. Welcome everyone out here. Hi positive, my dear lovely warriors. I hope I'm audible and visible to all of you. This is your Captain Shreyas on the Vedantu JEE English channel. Good evening, everyone. It's time to kickstart EMI, one of the major chapters. There will be one more class which will be happening on EMI, that will be on inductors, inductance, self and mutual inductance in the next section. All right. So going in detail right from zero to hero. So let's begin. And before we go ahead, make sure you have registered for MVSAT. In case you haven't, please do it right now. It is the Mega Vedantu Scholarship Admission Test, which will give you a clear-cut picture of where you stand in the actual competition, because the same people will be giving the JEE exam and the MVSAT. Lakhs of students will be giving it. So this will be a very true response of where you exactly stand. And if you're worried where can I register for it, as you're watching this particular video of mine, make sure you go into the description box of this particular video and you will see the link for registering for MVSAT right over here. Okay, just go over here and you can see MVSAT register now. Click on that particular link. All right, so you can register with your mobile number. And those of you who are interested in the JEE English batch, which is the Sigma Express, that link is also here. Today is the last day of the offer. In case you want to go from zero to hero, the batch is starting just 6 September. Right now it has started. And also the JEE Advanced Ekalavya batch for JEE Advanced properly is also there over here. So make sure you check it out. Okay. All right. Let's begin with the lecture. Now, what is this motional EMF? The name only carries some hint over here. Motion means it should be moving. EMF means it should produce electricity. So a moving conductor produces electricity. So does that mean if I take some copper and I move it, will it start producing electricity? The answer is no, only under certain circumstances. And what is that condition? That condition is basically it has to move in a magnetic field. Yes, Ibu, new intro. Oh, you guys noticed it. Very proud of you. I like your observation skills. So a moving conductor, not an insulator, conductor only, because the conductor can produce electricity, insulator can't produce such electricities. A moving conductor in a magnetic field, induces electricity. This phenomena is called as motional EMF. As you can see over here, this is a conductor, it is moving. You can see those lines, those is the magnetic field. It will induce an electricity, and the moment it induces an electricity, you will see one side will become positively charged, one side will become negatively charged. Maybe, just chumma saying, maybe one of this end will become positive and the other end will become negative. So it will generate a motional EMF. So there will be an EMF which will be generated across the terminals. Okay, so when you move this conductor, there will be an EMF which will be generated. One side will become positive, one side will become negative. We will see how to get the direction, etc. in a bit, don't worry. But yes, it produces EMF. It behaves like a battery. It induces electricity and behaves like a cell or a battery. Behaves like a cell. Now, why exactly would this be happening? What's the theory behind it? It's very logical, and let's understand it properly. Imagine I take a conductor over here. Okay, this is my conductor. Let's say this is my conductor. And now let's say there is a magnetic field. Let's say there is a magnetic field which is directed inside the plane of our board. There is a magnetic field which is directed inside the plane of our board. So I will call this magnetic field B. This particular conductor begins to move, say one particular way. Let's say like this. This is how the velocity is. It is having some kind of motion. All right. Now, as it begins to move, how is electricity being generated? That is the logic which we have to think. What is a conductor made of? Well, anything is made of atoms, molecules, right? And the more specifically for conductors, that atom has ready to give electrons which are called as free electrons, which can be easily mobilized. They can freely move within the space of the conductor. So let's look at one such atom. Let's look at one such atom out here. So imagine this is that particular nucleus of that particular atom, and then it has an electron cloud surrounding it. There is an electron cloud surrounding it like this. Okay, the central part obviously is the nucleus, which is positively charged. This is positively charged and this one is negatively charged. The green one is the nucleus, the red one is the electron cloud. So this is the positive nucleus and this one is the negatively charged electrons which are revolving around it. Now, these are both charged particles. Because the conductor moves, even the atom, the molecules themselves will have to move. So this will also have some velocity which is directed this way. Whenever you move a charged particle in a magnetic field, what happens? Immediately there is a magnetic force on it. So if you ask me on the positive charge, because of the velocity which is directed over here, Q V cross B, magnetic field is inside, velocity cross B will be a vector like this. So this is the force on the positive charge, which will be because of the charge of the nucleus into velocity cross producted with the magnetic field like this. Same time, the negative electrons, because they are also moving like this along with the conductor, because of that negative charge, the force will be exactly opposite. So this is that force on the negative charge. So it will be again the charge of the electrons into velocity cross B formula I have used. This, remember, is negatively charged. That's why the direction is opposite. So whenever you multiply a vector with a negative sign, the direction will invert itself. Instead of V cross B being upwards, now V cross B will be downwards because of the negative sign. Now, what happens is, this force on the nucleus cannot do much because nucleus, relative to the structure of the solid or whatever, it is stationary. So it cannot change places. If the nucleus moves, then the shape of the body will change, right? The major mass chunk of the atom is with the nucleus. So this force can't change the position of nucleus. Can't change the position of the nucleus. But the electrons, can you guess now what will happen? Everybody in the chat box, come on, think carefully. What will happen to the electrons? Of course, this force can mobilize the free electrons. Not all the electrons. The inner orbit will not be affected because they are held by the nucleus properly, but the outer electrons, which are relatively free, can mobilize the free electrons. So because of which, what do you think will happen? What do you think will happen because of this, my warriors? The nucleus everywhere will stay as it is intact. Let's say the nucleus here, 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 here will stay intact. But it is the electrons which will slowly start coming down over here. We'll slowly start seeing the electrons coming down like this because of that particular force. The positive charges haven't come down. It's the electrons which have started accumulating towards the downward side in this scenario. So indirectly, what will happen? Indirectly, what will happen because of this? I feel indirectly because of this. Indirectly because of this. Okay. Yes, the magnetic field is inside. Magnetic field is inside like this. So this side will become positively charged. This side will become positively charged. And this side will become negatively charged. So, because of this, there will be a electric field which will be created within the conductor from this side to this side. This will be an electric field which has been created because of accumulation of charges, because of charge polarization, charge polarization, charge polarization of the conductor. Polarization means separating. So you have separated the positive and negative charges because of the magnetic force, because of the motion, and that is why electric field has been created. Now, why is this electric field of particular importance? See, a lot of people think because of this magnetic force, all the electrons will eventually leave the respective atoms and accumulate on one side. So all the negative charges will be here and all the remaining positive charges will be on the other side. That is a wrong conclusion, because as and when electrons begin to move, there will be an electric field which is created, and that electric field will oppose the motion of the electrons. How? Notice what will happen. This electric field is downwards. But if you consider any kind of negative charge, the force on an electron, the force on a negative charge will be exactly opposite. It will be the charge into the electric field. Yes, it will be the charge into the electric field. It will be this way. Magnetic force is pulling it down, but electric force is opposing it. So there will be kind of an equilibrium which will be achieved. There will be a kind of equilibrium which will be achieved eventually when no further movement of the charges will happen. So eventually what happens is this particular conductor will reach an equilibrium with that positivity here and that negativity here. So there will be an equilibrium achieved in equilibrium which will be achieved in mobilizing the charges to polarize the conductor, to polarize the conductor. And when that equilibrium is achieved, you will see something like this. No further movement happens because the negative charge will experience a force this way of QE here and a simultaneous force of QV cross B over here. And remember, at the same time, everything is moving in this particular direction. There is an electric field which has been induced in this direction. Yes, this is that induced electric field, and at the same time, the magnetic field was directed inside. So the magnetic field was directed inside. So this is when that equilibrium is achieved. The net force on it will be zero. So the net force on the free electrons or free charges, I would say, free charges is going to be a big fat zero. So Once it is zero, it is reaching that equilibrium. This is that important word over here. And I can clearly say charge into the electric field, charge into the electric field will be nothing but charge into V into B into sine theta if required, but in this case it is sine 90. QQ cancels. So E will be nothing but V into B. E will be nothing but V into B. This V is velocity, B is magnetic field, E is electric field. Is that absolutely clear, everyone? Till this point, give me a thumbs up. All right. Gokul, we don't have so much of bandwidth right now because I'm completely involved in the batches, the Sigma batch, the DNA batch, plus we have the Vedantu JEE English channel. Plus, I was not seeing many students taking the NEET channel very seriously, not attending the live classes. So when we are putting so much of hard work, I expect some kind of sincerity and dedication from the students. So when we are putting that hard work on YouTube, giving that free content. So that is the simple reason, my dear. Okay, perfect. Now comes the most interesting part over here. Because of this electric field that you see and positive negative separation that you see, where does electric field go from? Always from the higher voltage to the lower voltage. So if you ask me, this is the higher potential, this is higher potential, this is higher potential, this is obviously the lower potential, this is obviously the lower potential. So clearly now we have the potential difference. So V stands for the potential difference in the conductor, potential difference, potential difference in the conductor, and this particular potential difference uh, this particular potential difference is then called as the motional EMF. This is then called as the motional EMF, which is introduced in that conductor. Isn't it amazing, guys? A motional EMF is nothing but that potential difference created because of the charge separation and the electric field, which happens because of the magnetic force on those mobile charges. It's crazy. Now, how much is this EMF? I'm interested. Not an issue. Voltage, electric field are related by the following equation. Electric field is nothing but potential difference per unit distance or for some kind of separation. So, can I not say over here this particular V into B is nothing but potential difference, which itself is capital V. This is capital V. Okay. And the separation is basically the length of this particular conductor. So let's say that length of that particular conductor is L. So that L will come over here. So if I move this slightly around, this particular voltage difference will be nothing but B, okay, into V, and then comes that length. Then comes that length. But usually we do not use that symbol V because it can be confused with the velocity. So I will prefer replacing this voltage. I'll prefer replacing this voltage symbol with E, that is better, so that there is no confusion at all. So now it looks easy. So the EMF induced is B into L into V. Very interesting derivation. Did you love it? How motional EMF comes out to be, that voltage difference comes out to be magnetic field into the velocity into the length of that conductor across which the charges have been separated. Yes, definitely, Praha, you can definitely watch these classes for NEET, JEE, CET, anything. But obviously, these are JEE oriented classes, so it will be maintaining that standard. But sir, tell me one thing. Okay, before going there, I just wanted to also tell you that a moving conductor in a magnetic field can be treated like a battery, just like I had shown over here. Where did it go? Yes. A moving conductor in a magnetic field behaves like a cell because it produces voltage difference, okay, and it has some EMF across it. So that's the reason why I'm mentioning this particular part over here, that yes, that moving conductor can be treated like a battery in a part of a circuit if it is connected via wires to some bulb, resistor, inductor, capacitor, doesn't matter. So it can be definitely treated like a battery whose EMF is BLV. But there is one small thing over here. One second. There is one small thing over here. Can we look at it using some other principle? Can we look at motional EMF using some other principle? Yes, the answer is yes. Let me see how. One way to look at motional EMF was seeing how the free charges get polarized inside the conductor, produce electric field, and thereby create EMF. But there is also an alternative way, and that is via Faraday's law. I'll tell you how. Just look at this. This is a conductor. It is moving inside a magnetic field. The magnetic field lines are probably not seen, but yes, they are like this. Okay, the magnetic field lines are over here like this. Say, for example, as this conductor moves, there are wires which are connected across the ends of that conductor like this to a resistor. Now look at this part which is over here. Just concentrate your focus on this particular segment. Tell me, is the area reducing or changing, yes or no, of this particular circuit? Obviously, the area enclosed is definitely changing, and because of that the magnetic field lines which are passing in this area, that will reduce, thereby the magnetic flux is definitely going to change. Definitely magnetic flux is also changing. Because of this, what will happen? We have to use which law? Faraday's law. By Faraday's law, and also Lenz's law gives me the direction, and Lenz's law, what do I get? I can immediately say there will be an induced EMF. There will be an induced EMF which then can be treated like the motional EMF. Which can be then treated like the motional EMF. You can very easily see, because the magnetic field inside is reducing, because as the rod goes here, the flux will reduce. So the induced EMF should be such that it will help, it will strengthen it. So the magnetic field being inside, to strengthen it, you have to create a magnetic field inside of it to help it. So if you hold the thumb in that same direction, my fingers of the right hand will curl in the clockwise direction. So you will see that the induced EMF will be in the clockwise direction. So it will be in this direction. That means the current will be supplied like this. So this particular rod that is there, that particular rod will behave like a battery like this. Is that clear? Motional EMF, exactly what we predicted here also. It was behaving like a battery with positive terminal here, negative terminal here. So exactly same thing it is doing. It is behaving like a battery of some EMF. This EMF can be found using your principle of d phi by dt, magnitude wise. We can use Faraday's law, we can use d phi by dt and easily get it. It's not a big deal because flux is nothing but B A, that's it. But magnetic field is constant, so bring it outside. So it will be just area, and area is nothing but length, and area is nothing but length into x. Now you might be wondering what the hell is x over here. So let me mention that. Say for example, this is your length, already mentioned. This is your length. this is your length, right? And let's say this is your x. Okay, this is your x. So the area is length into x, but length is also constant. It is not changing. Only this x is changing. So what will be dx by dt? What will be dx by dt? Think about it. What will be dx by dt? It is going to be velocity. So it will be bl into v. Exactly what we got over here. So whether you go via Faraday's approach or via the fundamental principles of magnetic force, you are bound to get the same answer. That is what I wanted you to see. Amazing? How many of you found this amazing thing? And I'm pretty sure many of you wouldn't see it exactly this way. Yeah. Ray optics, you can watch my older classes, Uday, or you will have to wait for next week. Next week, I'm going to start with ray optics. Okay. But you can watch my older classes of Nurture Pathfinder. Awesome. Now that we understand it, how Faraday's law can also be used for deriving the same motional EMF, the only thing left is the vector form, which will help me with the direction. And this vector form is very important. Lot of students don't even know that there is a vector form. They just remember BLV. That's not right, because not every time it will be BLV. It could be BLV sin theta, cos theta, something like that. So the actual true form of getting that EMF, of getting that particular EMF is, first of all, remember EMF is a scalar quantity. So the vector form has to be some scalar operation. So what you have is the length over here, the length of the conductor along which you are measuring that EMF, dot producted with, you take the velocity of that conductor and cross product it with the magnetic field in which it is moving. That's it. So first you do the cross product. So that will be a vector. When you do the dot product, it will become a scalar quantity, which kind of makes sense. And now this is the final form. So please remember this particular form. Over here, I have also put V cross B dot L because dot product is commutative. So whether I do L dot V cross V or V cross B dot L, it really doesn't affect my final outcome. Okay, it's a commutative property, right? Dot product. Okay. So this is very, very important. How to analyze this? Imagine you have some kind of conductor of any random shape and you are taking some 2 points somewhere which are then separated by a distance of L, and this particular conductor is moving with some velocity v in some magnetic field like this, So when you do V cross B, V is here, B is inside. So you're going to get V cross B over here. This will be the vector of V cross B. Just think about it. V is right side, B is inside. So the thumb will go upside. You now take the dot product with L vector, this V cross B with L vector. So that dot product is what is happening here. That will give me the EMF. Is this now absolutely clear? This is now taken as a dot product with L. That's it. That is what will give me the answer. Everybody clear about it? Okay. Now please remember, how do I know whether it is positive or negative, or which side is positive voltage, which side is negative voltage? Can you take a guess, my dear students? Yep. Can you take a guess? It's very simple. If you take the L vector like this, because L is a length, I can take it this way also, this way also. Then this dot product will obviously be positive, isn't it? This dot product, because the angle over here is acute, this dot product will be positive. That means this is the correct direction of EMF. That means this side will be positive, this side will be negative. That means you can assume the battery to be like this. This side will be positive, this side will be negative. But some hero V cross B is like this. Some hero doesn't know. that actually I should take length this way or this way. So that person takes the length like this, because length actually does not have direction. So you can take either way. So if that person chooses the length to be this way, then this dot product will be negative because this angle is obtuse. So this will be negative in nature. That means this direction is the wrong direction. So do not choose that. So do not choose this side as positive and this side as negative. Don't do this. This is not going to be positive and negative. This is wrong. This is wrong. But this is correct. So you have to flip the terminals. Magnitude wise, it will be fine, but direction wise, it will be wrong. Is that understood? How to decide which side is positive terminal, which side is negative terminal? Everyone, give me a thumbs up in the chat box right away, right now. Okay, sir. Let's go to some cases and let's figure out what might be the motional EMF in all these scenarios. Like take this example, magnetic field is inside, the length is here, V is here. Which side is positive, which side is negative? Same thing here and here. Okay. Now, velocity is right, magnetic field is inside. So V cross B, of course, will be like this. V cross B will be like this. If I choose my length vector to be in this direction, then the dot product will be positive. It means if it comes out to be positive, that means this is the correct way of orienting it. So this side will be positive terminal, this side will be negative terminal. So this rod will have this side positive, this side negative, if you convert it into a battery of EMF E. Let's take this scenario. Velocity is here, magnetic field is inside. So again, my V cross B vector is going to be here. V cross B vector is going to be here. But the funny part is my length vector is going to be like this. Whether you take here or here doesn't really matter. The dot product is just going to be a big fat 0. Yes, because the angle is 90 degree. So dot product. So the dot product will be 0. The dot product will be 0. So there will be no EMF in this scenario. There will be no EMF in this scenario. Is that absolutely clear, everyone? Isn't it amazing? Okay, so no EMF even though there is a conducting rod over here, because the EMF will be developed in this direction, not in this direction. How about this scenario where the length is making an angle with the velocity? That scenario can also come. So what to do? Well, V cross B will again be upwards. V cross B will again be upwards. My length vector though will be like this. And the length vector is making an angle with the velocity. So how much will this angle be? Just think about it, my dear warriors. How much will this particular angle be? This particular angle will be 90 minus theta. This will be 90 minus theta because theta is with the horizontal. So with the vertical, it will be 90 minus theta. So if you ask me the EMF, it will be L into V cross B, which is VB, into cos 90 minus theta. Into cos 90 minus theta. What is cos 90 minus theta? Sin theta. So it will be LVB sin theta. That will be the EMF. That will be the EMF. LVB sin theta. Clear, everyone? Absolutely. Shall we go ahead now? So in all these scenarios, now you can figure out what the direction is. Okay, by the way, this angle was acute. So it's also obvious that the battery that I will assume will be in this direction, with this side positive, this side being negative. That is the right way. Here, so there is no EMF. Here, there was EMF. Perfect. Now, let's see what to do if the wire is made of some random shape, not a straight wire. Imagine it's a curved wire or a bent wire. Hi Tech Gaming, hi Divine. Welcome aboard everyone. Very good and me. So in that scenario, what do we do? Imagine you have some kind of a wire like this, a curved wire which is translating, a curved wire which is translating like this with some velocity v in some magnetic field, uniform magnetic field, in some uniform magnetic field like this. So this is uniform magnetic field. Then the problem will be you have to split the wire into small parts to find the EMF. So the EMF in that curved wire will be the sum means integration of the small EMF in all these elements, small straight elements, which will be there. You have to add that up, the small straight elements. But that will be problematic. I don't want integration. But the best part is that integration becomes very simple. We don't have to go into the derivation and all that. Even though if you go, it is simple. The answer is that this particular EMF which is there in that curved wire comes out to be, if you join a straight line, imaginary straight line, this is between the ends of the conductor and the length is L, then that EMF is the same EMF as a straight wire conductor connecting the ends. So it will be as simple as L dot V cross the magnetic field. V cross the magnetic field. That's it. This L then becomes our effective length. That's it. So just join a straight wire connecting the ends and your job is done. It's so easy peasy lemon squeezy. So that is the EMF of a curved wire. Okay. So I'm going to block this up. So the EMF of a curved wire in a moving in a uniform magnetic field is that of a straight wire of length connecting the ends moving with the same velocity in that same magnetic field. Very easy peasy lemon squeezy. I think this kind of theorem we also studied back in magnetic force. Remember, if there is a curved wire carrying some current, the force experienced by it is the same as a straight wire carrying that same current in the same field. Very similar. All right. Okay. Astrophysics talks, but I didn't expect that you would do that video. I'm so glad. That was the whole purpose, IITian. I mean, a lot of times we just get so involved into teaching, we stop exploring. And that was also to generate that kind of curiosity in all of you. It's not about whether it will happen or not happen. That's secondary, but also talk about it to explore different things around us. Sir, if that is the case of a curved wire, then tell me what will happen if I have a loop? What will happen if I have a loop? This is a loop. This is conducting loop. There is a conducting loop which is translating in a magnetic field. Now, whether you go via this theorem or even via Faraday's law also, you will get the same thing only, because there is no flux change. Also, the effective length, because there is no end over here or no start, or if you take a start, the end is the same point. So the effective length will be a big fat 0. So hence that EMF will also be 0. So in a magnetic field, will not have motional EMF. One condition though, this is not any magnetic field, this has to be uniform. If it is non-uniform, it can produce. Please remember that. Okay, all the theorems are for uniform magnetic field only. Okay, so is this absolutely clear? If you take a loop and you move it, obviously there is no change in flux, the effective length is 0, so there is going to be absolutely no EMF which will be generated. Okay, perfect. Having said this, I think it's a good time that we start with some questions so that we get a hang of it. Here comes the first question. It's a very laddu question which was asked in JEE 2023. Let's see. An EMF of 0.08 volts is introduced by a rod of 10 centimeters, which is held normal to a magnetic field when it moves with what velocity? So our rod is like this and it is moving like this, and the magnetic field is like this of 0.4 Tesla. The velocity is what is asked. The length of the conductor is 0.1 meter, and the EMF which is developed is given to me as 0.08 volts. In this scenario, it is obvious that velocity cross magnetic field, velocity is here, magnetic field is inside. So V cross B will be like this, and the length vector will also be like this. So there is no angle between them. So when you do the dot product for L dot V cross B, so when you do the dot product for L dot V cross B, the dot product of cos 0 will become 1. So it will just simply become BLV then. You don't have to do anything. It will just simply become BLV. Okay. So where is it? Yeah, over here. This will be just B into L into V. EMF is 0.08. Magnetic field is 0.4. Length is 0.1. Velocity is unknown. Therefore, velocity will be, this will be 8 into 10 to the power negative 2. This will be 4 into 10 to the power negative 2. So 8 by 4 is 2. So velocity will be 2. Everything is SI units. So 2 meters per second, which is option B for IIT Bombay. Is that absolutely clear? Very simple question asked in JEE 2023. Very good, Korao. Welcome, Anjali. Hi, Ashwita. Very good, IITian. Yes, that's option B. Very good. Let's move to the next question coming up on your screen. This was asked in 2021. Again, an introductory question just to get you a feel, a sense of how much this voltages and values are. Aeroplane is there. The wings have some speed moving with, that speed is given. Intensity of the Earth's field is given, and the angle of dip is given. The induced EMF between the tips of the plane and the wings will be. Very interesting question. So let's assume that this is the wings of that aeroplane. Okay, that aeroplane could be maybe like this. We are not bothered about the other parts of the aeroplane. Okay, we are considering only that main big wing. That aeroplane is going like this. Okay, are you able to visualize this, my dear warriors? Yeah, the aeroplane is going like this. Okay, this is the velocity. Now that velocity is given to be 180 kilometers per hour, which is 180 into 5 by 18 meters per second. 180 by 18 is 10, so 10 into 5, that's 50. So 50 meters per second is that velocity that is needed, because we'll do it in SI units. Don't worry about this. This is also Tesla. Weber per meter square is nothing but Tesla. So don't get scared, sir. What kind of conversion do we need to do? 1 Weber per meter square is 1 Tesla, which is a SI unit again. Okay, the Earth's magnetic field and the angle of dip. This is very critical. See, the angle of dip means the angle which the magnetic field makes at that particular place. So strictly speaking, the angle which the magnetic field is making with the horizontal line is given, and that is 60 degrees, I believe. And the magnetic field is 2.5 into 10 to the power minus 4 Tesla. Is that okay? 10 to the power minus 4 Tesla. That is also given. First things first, let's do V cross B. Where is velocity? Here. Where is magnetic field? Down. So where will be V cross B? Think carefully, guys. Where will V cross B be? Yes, the V cross B will be directed inside. Velocity is there. Magnetic field is directed. Dip angle means how much are you dipping? I'm rising, I'm dipping. Dip angle. So dip angle is given to be 60 degrees. So that is always measured with the horizontal. So basically, if I do V cross B, my thumb goes inside. So this is where my V vector cross magnetic field will be. But my length of the wing is also going to be inside. length of the wing is also going to be inside. So the angle between both of them, is 0 degree. So cos of 0 degree is 1. Why did I take cos 0? Because I have to do the dot product of length and V cross B. So the dot product will be LVB cos 0, like that. But the problem is this V cross B. Remember, velocity and magnetic field themselves have some angle. So if you ask me how much is this magnitude, it itself will be VB sine of the angle between them, which is VB sine 60. VB sine 60. So that is the interesting part about this question. So the EMF will be, you will have your length, but the dot product which was there will be cos of 0. Okay, then that V cross B will be VB sine 60. So you should understand that when you use this vector equation, this cross will have sine theta part, the dot will have cos theta part. Sometimes both of them are 1, sometimes one of them is 0. So you have to think from situation to situation. In this particular problem, we saw that the cos 0 is 1, so the dot product was 1, but the cross product was sine 60, was having that term sine 60, because angle between velocity and magnetic field was 60 degrees. Now it is easy to solve. Let's find out. What is the length? Length of the wingspan, I think, is 10 meters. Okay, can you see that? It's given right over here. This is 10. Cos of 0 is nothing but 1. Okay, what is the velocity? Velocity is given to be 50. Magnetic field is given to be 2.5 into 10 to the power minus 4, and sine 60 means root 3 divided by 2. That's it. So that will give me the final answer. Come on, calculate this and tell me how much is it coming out to be. This, forget this decimal with 0 or with the 10. So it will become 25. 25 into 5 will be 125. 125 divided by 2 is 62.5. 62.5 into 1.732. Come on. That root 3 will also be there. Tell me the answer, guys. Some people are saying IIT Delhi. Okay. What about others? Yes, 108. Looks like it. Should be, maybe. This will be 108. Maybe. Yeah. 108. 108 something is coming. Everyone? Yes, 108 millivolts. Just check this out. Yes, 108 into 10 to the power minus 3 volts, which is option D, of course. Yep, IIT Delhi. Amazing, amazing. Very good. So this was a good level question. Even if you think that it was simple, the catch was, where is that angle coming? It was not coming here, but it was coming between velocity and magnetic field, which is little unusual. Next, let's go to the next question coming up on your screen. There is a square loop of A side which is moving with a constant velocity and passes through a magnetic field B as shown. Now, I don't think you're able to see that magnetic field. So let me just mark it over here. This is where that magnetic field is present till here. This entire region has some kind of magnetic field. Okay. As you can see, it first is outside, partially inside, completely inside, partially outside, and then it completely comes out. Are you able to see that? One small shading I have done. Okay, I will box it out so that it is very, very clear. I'll box it out so that it is clear. Okay, so in this box, magnetic field is present. So find the direction of the induced current in this particular scenario. You can do it by Faraday's Lenz's law, or you can do it by motional EMF also. I mean, just think carefully and over here, when you are completely outside, there is no magnetic field, there is no change of flux, there is no question of motional EMF. So here the EMF will obviously be zero. The EMF will obviously be zero. Is that absolutely clear? Okay. I can do it by flux, but I'm not doing it by flux because I'm teaching motional EMF. Let's look at this scenario. This part will obviously not produce any kind of EMF. So let me just ignore that part. This part, oops, this particular part will not produce any kind of EMF. I feel even this part will not, even this part will not. Okay, same thing, this part will not produce any EMF because there is no magnetic field in that region. Even this part can't, and even this part can't. Now the problem happens only with those parts which are inside the magnetic field. They will definitely have some kind of EMF within themselves. So if you consider this vertical elements like this one, or even this one, or even this one, think carefully, those are conductors which are moving like this in a magnetic field which is directed inside. So if you do V cross B, it comes up. So the length vector, if it is taken up, the dot product will be positive, which tells me that this side will be the positive, this side will be the negative side. So I got the direction of the EMF. So upwards is positive, downwards is negative. That means these people over here, like this one, or even this one, or this one, or this one, all of them behave like batteries like this. Behave like batteries like this. Are you able to visualize it? Even this one behaves like a battery like this. All of them. Okay, because of this reason, L dot V cross V. But what about these horizontal elements? That is another interesting aspect over here. Observe carefully. If you look at the horizontal elements like this one, or even this one, or even this one, or even this one, or even this one. Okay, what you will see is any of these elements whose length is like this in horizontal direction, yes, their velocity is here. So when you do V cross B, magnetic field is inside. The V cross B vector comes up. So when you do the dot product with length, the answer will be 0. So it will not produce only any kind of EMF. So the EMF in that part will be 0. Are you getting my point? Velocity is right, magnetic field is inside. So when you do the dot product, it will come up. So when you take a dot product of this vector with length vector, angle is 90, cos 90 is 0. So no EMF will be produced. So 0 EMF. So I'm just showing it like a wire. So this is how the correct diagram will be of the EMFs being developed within the circuit. Hi Shivanshi, welcome. All right. Arivaransu, definitely I'll make a video on that. Hi Sophia, welcome aboard. Now imagine this. Once I've deduced till here, if I ask you what is the direction of the current, it kind of becomes obvious that over here there is no EMF, so current is obviously not there only. No point talking about current. Here there is only one battery and these are all wires. So the current obviously, because of this guy, will move like this in the anti-clockwise direction. This is how the current will be anti-clockwise. Here the battery is like this, so current will be supplied in this particular direction, which is obviously clockwise. Even if you go by Lenz's law, you will get the same answer. What about this scenario? Answer it in the chat box. What about this middle scenario? Yeah, this battery is trying to supply the current like this. This battery is trying to supply like this. They both will oppose, and guess what? The net current in this part will be 0. And flux actually is not changing, so current should not be there also. Yes, EMF is there. It's like two batteries which are connected in the opposite directions. So this is also trying to push, this is also trying to push. They will cancel and net EMF will be 0, net EMF. And also the current will not flow because of this dog fight or whatever tug of war which is there. Okay, everyone. So this is a very interesting theory of how via motional EMF you are analyzing this scenario rather than using your flux change and Faraday's law and Lenz's law. Cool. Let's go to the next question coming up on your screen, and this is based on the same scenario. You have a region where there is magnetic field. This is that region of magnetic field, and that square loop having some turns and some resistance is placed. Find the EMF in the left arm of the loop as it is pulled out of the field slowly in 1 second. Okay, as it is pulled out slowly in 1 second. Interesting. So if this particular loop is being pulled out, think like this. This loop was here and finally it is out like this. This is the ending part. This is that ending part. So my loop has moved this much, which is having some area, some turns, etc. Okay, we can find that length. We can find that length. In 1 second, you have moved it. From this, we can get the velocity. From this, we can definitely get the velocity. From this, we can definitely get how much EMF was there over here. There will be some EMF. We can easily get that EMF, which will be L into V into B. Now, how much is that length? I do not know. How much is the velocity? That also I do not know. How much is the magnetic field? I think that I know. Magnetic field is given. I think the area is given for that reason only, because from that area, we can figure out, from that area, what can we figure out? The length. Yes. So what is that formula? Area is length square. So it is 2.5 into 10 to the power minus 3 is length square. So it is 25 into 10 to the power minus 4 is length square. So length will be square root of 25 is 5. 10 to the power minus 4 square root is minus 2. So this much is the length. From this, we can figure out velocity. Velocity is length by time. This much distance in this much time. So length is 5 into 10 to the power minus 2. Time is 1 second. So it will be 5 into 10 to the power minus 2 meters per second. Right? But that's not all. This particular loop has 100 turns. Some resistance is also given. Find the induced EMF in the left arm of that particular loop. Each length will produce this EMF. So this is basically per conductor. Remember, there are many turns, so there will be n such conductors lined up because there are turns over here. You can see many such conductors are there because they are all coiled up. So n into LVB will be the net EMF. So number of turns is 100. The length is how much? 5 into 10 to the power minus 2. Velocity is also 5 into 10 to the power minus 2. And magnetic field is 0.4 Tesla. Magnetic field is 0.4 Tesla. That's it. That will be my answer. 5 5s are 25. 25 4s are 100. But because of the decimal, it will just become 10. Then you have this 100 and 10 to the power minus 2 will cancel out. Only one 10 to the power negative 2 will remain over here. So if you want, I can also write it as 100. This is nothing but 100 into 10 to the power minus 3, which is also 100 millivolt or just 0.1 volts. That will be the answer. Is that absolutely clear, everyone? With me? Yes. Sir, in Jan attempt, I want to score 175. Okay, CRL, please give me weightage for just entry, not for IIT. Oh my God, Kevin, that is a very mediocre target and you're underestimating yourself. I don't know why you want such a low rank, but yeah, I will be giving the weightage of the chapter list very soon. Don't worry. Okay. Yes. All right. So that is the answer, 0.1 volt. Perfect. Let's see the next question coming up on your screen. Here it is. A rectangular loop which is there is moving out of a magnetic field. Question is, when the loop is partially inside, plot the magnitude of the EMF with the time. plot the magnitude of the EMF with the time. That's the question. Let's see if you can figure it out. Okay. Yes, Aswita, I'll be making a separate video on that. All right. Hi, Divya. Welcome aboard, everyone. So this question directly related to this question. Where is it? This, you're pulling it out, or even this question, the same question. When this was happening, velocity was same, magnetic field was same, length was same. So the EMF was same as you are pulling out the loop. So EMF did not change, so it will be constant. So I think that constant graph should be there, which is this one. Nor this, nor this, nor this. Yes, the EMF will be constant as long as it is being pulled out. Once it is out, it will drop down to 0. Once it is completely in also, it will be 0. Only while going in or coming out, which is exactly what we discussed right over here, right? Only while going in or coming out. When it is completely in or completely out, there is absolutely no EMF. And which part produces EMF also I have discussed over here. Cool? Yeah. Awesome. Awesome. Great. Let's go now to the next amazing question on your screen, and here it is. A copper rod of some mass slides under gravity because of two smooth parallel rails with separation L and set at an angle of theta with the horizontal. At the bottom, the rails are joined by some resistance. There is a uniform field normal to the plane of the rails as shown in the figure. I think it's not there, but we'll draw it. Find the terminal speed of the copper rod. Very interesting question. Let me first, first I will draw one diagram here, then we'll go ahead. Okay. These are the rails like this, and they are connected by some resistance at the bottom, and this is the ground level. That rails are making some angle with the ground. That angle is given to be theta. Try to visualize this. This is an inclined plane. The inclined plane has two rods which are like rails, and those rails are making some angle theta with the horizontal surface. At the bottom, the rails are connected by a resistance of R. That is what is given. Okay. Now there is a rod which will slide on it. Okay. Let me show that rod. That rod is over here. This rod is going to slide down like this along this inclined plane. Okay. With some velocity V. Okay. And there is a magnetic field normal to the plane of the rails, meaning the magnetic field is like this. You'll have to visualize this really. This is how, but the magnetic field really is crazy. It's at some angle and it is perpendicular to the rails, as you can see over here also. Now it is coming down with some velocity. Question is, find out that velocity with which it comes out. Now, one interesting word over here is terminal velocity. Terminal velocity means that velocity which is finally achieved and it does not change. So that means we have to assume that this word refers to one constant speed which is achieved. Constant speed which is finally achieved. And the moment I hear the word constant speed, I immediately think of no acceleration. No acceleration. And whenever there is no acceleration, that means net force on the rod is absolutely zero. Net force on the rod is zero. That means all forces are balanced. All the forces on the rod are going to be balanced in nature. So we need to figure out what those forces are. Is that clear? If we get that, I think my job is done. So this is how you solve the problem step by step. You have to look for clues within that statement, problem statement. Okay, now let's think. What kind of forces are there? Okay, fair enough. I will look at the side view of this entire scenario. And the moment I look at the side view, I see the rod going in and out. I can see the inclination being like this, making a certain angle over here, which is theta, The magnetic field is like this. The magnetic field is like this. Okay, I'll keep that aside, but it is not a force, mind it. Now let's see what are the forces actually present. First force is the weight itself, and mg will be downwards. Mg will be downwards, but I can split mg into two components. One will be like this, and the other one will be like this. And we know by experience that if weight is like this will be mg, because this will be also theta. This will be also theta. This will be mg cos theta, and this will be mg sine theta. This will be mg sine theta. Okay. Apart from that, there will be a normal force on that rod like this. No friction, I believe, because smoothness is mentioned. So no friction. So there must be something to balance mg sine theta, because normal is getting balanced by mg cos theta. Remember, eventually all the forces should be balanced on the rod. So what are we missing? I know what we are missing. This rod is not just a rod, but it is acting like a battery. How many of you realized it? Yes, this is no longer just a rod, rather a battery over here. So V is here, magnetic field is here. So I think velocity cross B, if you do, it is going like this. So it is now actually, forget that velocity also. Forget this velocity also. Think of it like a battery. Yes, of some EMF. And that EMF is creating some kind of a current over here. And there is obviously some resistance over here. Because of that current, this rod is experiencing a force of ILB. Oh, what a concept. Imagine a current carrying wire in a magnetic field experiences ILB force. And that is that force which might be balancing it. Okay, so let's go step by step. Let's not hurry. So to find the force, I need the current. And to find the current, I need the EMF. And this EMF is no ordinary EMF. Rather, it is motional EMF. Which EMF is it? It is, strictly speaking, motional EMF. It is your motional EMF. Yeah. So that moving rod in the magnetic field is producing motional EMF. So velocity is down, magnetic field is up, V cross B goes inside. Check that out. Let's go step by step over here. Let's not hurry. Okay. So my velocity is over here. Magnetic field is like this. So V cross B goes inside, which is also the direction of the length vector, The angle between the magnetic field and velocity is 90 degree. The angle between length vector and V cross B is 0 degree. So if you ask me what is the motional EMF, it will be L. Dot product will be cos 0, and the cross product of V cross B will be VB sine 90 degree, because angle over here is 90 degree. Can you see that, everyone? Yes, that is 90 degrees, as you can see over here. Okay, so how much is this EMF coming out to be? This is L, this is V, and this is B. That is your EMF. So current will be EMF by resistance. So therefore current will be LVB divided by resistance. Okay, so I found out the current Most of my job is done except for the force. So current is like this. In fact, it is going inside. So if I do IL cross B, IL cross B, length is inside, cross B, it will go this way. It will basically go which way? IL cross B will be like this. This is where my ILB force will be. Current is inside, magnetic field is up at an angle, so thumb will go up the inclined plane. So because the forces are balanced, my ILB force should be balanced by mg sine theta. So therefore mg sine theta will be current, which is LVB by R, LVB by R into L into B. But question is, what is the speed, right? So velocity will be M into G into R into sine theta, whole thing divided by L into L is L square, V is on the top only, B into B is B square. So mgr sine theta by B square L square, which is option number B. Yes, which is option number B, of course. Yep, everybody, isn't it an interesting question? Yeah. Teamwork, we have already made that batch. It is called Sigma Express. I'm not really sure if you're aware of it. If you're not aware of it, please check out this video. The Sigma batch, which is there, it is exactly that one-shot batch, but it is not complete one-shot. The people who miss Sigma batch, the remaining classes will be taught properly live. Live is in detail. That part which you have missed will be taught in one shot. So rather than doing entire syllabus one shot, you have the time, September, October, where you can do properly, at least 10-15 chapters you can do properly. So the remaining 10-15 chapters, you can do it in one shot live. That will be also a part of this batch only. Got it? So this batch link is there down in the description box. Please buy this batch, Sigma Express. Okay, this is that fresh batch. Cool? All right, teamwork. Sir, the Unit 2 video which you made on Vedantu Tamil channel was so damn good. 3 hours feels like 30 minutes. I'm so glad, Peter. Yeah. Yeah. So when the time comes, definitely I do the CBSE part. Okay. Thank you so much. All right. Let's go to another question coming up on your screen. This was in JEE 2023. This is a rod which is rotating in a magnetic field. And the question is, find the induced EMF in this. Now you might be like, what's so great? It's just a rotating rod, so BLV. But then, if you think deeply, you will understand, oh, wait a minute. BLV, B I know, L I know, V. Which velocity should I take? Why? Which velocity should I take? This is a rotating rod, and a rod rotates. Every point has a different velocity. Oh, the point which is at the axis has 0, point which is here has maximum velocity. So should I take average? Don't do that stupidity. Never do that. Okay, because we do not know whether it should be average or square average. Who knows? So better to go by proper basics. Okay. So if I take this particular rod over here, okay, this entire rod has some length, L, and it is rotating with some angular velocity. What I do, I will take a small part of that rod, could be any part. Maybe this part over here. This particular part from the axis is at a distance of x and has a width of dx. It has a width of dx. Okay. This dx part will have some velocity. Obviously, different parts will have different velocities. That velocity will be angular speed into the radius. The radius of this circle will be x. So it will be omega x. If I take this part here, it will have more velocity. This part here, even more velocity. This part here, less velocity. So now I have taken care of that part where velocities could be different. at different places, which kind of makes sense. Now, what do? I will say what will be the elemental EMF D. That elemental EMF D will be length, which is dx, into V, which is here, into magnetic field. But that velocity itself, I told you, it is omega x. That velocity itself is omega x. That is that small EMF D. So this small EMF is here, small EMF here, everywhere small EMFs are there. So if you think about it, this entire rod is made of all such small EMFs, right from here till here. Each one is D. So to find the net EMF, all these batteries are in series. You can see this is series combination. I just have to add the EMFs. So it will be integration of D. So what is integration of D? That will be, okay, wait a minute. This omega and B will go outside, bro, and only X and dx will stay inside. That will give me the net EMF. Perfect. But the problem is, what are the limits of the integration? Think about it. Well, start from here, end over here. When I start, my value of X will be 0. And when I go here, the value of X will become the entire length of the conductor. So this will be obviously 0 to L. X's integration is X square by 2. So it will be L square by 2. Here it will be 0 square by 2 after putting the limits. You have to subtract both of them. That's it. So this EMF will be B omega L square by 2. Now, this formula, don't have to derive it every time. Better remember it, because these questions get repeated. Rotating conductor is a common question in JEE mains or even in advanced. B omega L square by 2. Clear? So the answer is half B omega L square. Now this same question, I think, again got repeated in value form in another year, JEE 2022. So I am giving it to you as homework. A rod moving with some angular velocity, horizontal field is this much, the induced EMF in the ends of the conductor. It's the same kind of thing. It's just that the rod is rotating in a vertical plane. So instead of rotating like this, it is rotating like this. Okay, it is rotating like this. And the magnetic field is here. So again, the magnetic field is perpendicular to the plane of rotation only. So if you look at this diagram and this diagram, the one where it is rotating like this, it is the same thing. I mean, it's not any different. So the value will come out to be very easily similar to this one. You just have to substitute the values, omega, L, B, everything. So this is your homework question. The answer is there on the next slide. You'll be getting the PDF in the description box or the comment section. It will be pinned over there. Okay. So get it later on. For now, I'll not show you the answer. That is your homework. Post the answer in the comment section. Cool. Everybody, till this point, absolutely clear? Perfect. Yes. Now, let's take another interesting question. Let's take another interesting scenario of this motional EMF, where sometimes, imagine this is asked. There is a rod here and it is hinged somewhere over here, moving with omega. This is L, and let's say this is 2L, 3L, 4L, anything, or this is 3L, this is 2L, whatever. Now, again, there is a magnetic field over here. Magnetic field is there. Question is, what is the EMF across the ends? Question is, what is the EMF across the ends? What is the EMF across the ends of the conductor? A very interesting question, guys. Okay, very interesting question. Let's see how do we do it. I'll tell you what. Break this problem into two smaller parts. Just now what I showed you was, if there is a rod which is rotating about an end, what is the EMF? So what I will do, I'll break it into two rods. I'll break it into two rods like this. This particular rod over here and this particular rod over here. This is hinged over here. This is hinged over here. This is rotating with omega. This is also rotating with omega. This is having length L. This is having length 2L. Okay. So now what will happen is this rod will behave like a battery, like this EMF. But since the length, everything is more, it will be like a bigger battery, I would say. Correct? And that EMF will be half B omega L square, which is 2L square. This rod will also behave like a battery, but it will be facing exactly opposite direction. That is the most important part. And this EMF will be half B omega, this will be just L square. Now these two batteries, if you combine them together, how will it look like? Well, there is one battery facing like this, and then there is another battery which is facing like this. So what will be the EMF across the ends of the rod? Will it be E1 plus E2 or E1 minus E2? Obviously, it will be minus E1 minus E2 because they are opposing in series. They are opposing in series combination. So you have to consider the sign. So this will be nothing but B omega by 2 is there. You will have 2L square minus L square. That's what you will get. So 2 square is 4, 4 minus 1 is 3. So this will be 3B omega L square by 2. That is the net EMF across the ends of the rod. This kind of question can be one of the tricky questions asked in JEE because the rod is not pivoted at the end. It is pivoted somewhere in middle. Is that okay? Oh, Kevin, that is amazing. And I had many such examples, I can tell you. In fact, some of my friends too, who are in NIT Nagpur, they became pilots in the Indian Air Force. Some of them also became commercial pilots. And this is some very interesting discovery which people encounter after studying or during the process of engineering, that okay, I want to do something else only. And that is something which you should definitely follow and pursue. Don't think that, oh my God, I studied for JEE and I'm in an IT or IIT. How can I go here or there? Don't think like that. If it is your passion and if you want to become someone, please go for it. Okay, I missed out on that opportunity because of that age factor. If I'm not wrong, it was 22 or 23 years old. But otherwise, I was all fit, hale, and healthy. No eyesight, no color blindness. Height was perfect. Body was perfect. Everything was fine for me. Yeah, just that age factor I missed out on. So if you want to become one, please go ahead with it. Yeah. What about 3i Atlas, Mr. Beast? Have a look at the video which I made. Yeah. All right. Cool. So now let's go to an interesting concept of induced fields. What the hell is this? Induced electric field. Okay. Now, let me answer or let me ask you a simple question. Imagine there is a actual conducting coil. There is an actual conducting coil. And let's say there is this magnetic field which is there. Okay, there is some magnetic field which is over here. This field is changing. There is a field which is changing. There is a field which is changing. Okay, fair enough. Now, because this magnetic field changes, what will happen? Very clear and obvious thing. Whatever field will pass through that particular coil, that will create a flux. So therefore, the magnetic flux changes. The magnetic flux is definitely going to change. Because the magnetic flux changes, by Faraday's law, there will be induced EMF. There will be induced EMF. That means there will be a potential difference in the coil. Potential difference in the coil. And because of this potential difference, there will be induced current, induced current, whose value can be given by the induced EMF divided by the resistance of that particular coil. Very simple and straightforward, isn't it? There will be induced current which will be there in the coil. Okay. Now I will do one thing. I will just say there is no coil, but this is an imaginary path. This is an imaginary path or a loop. Imaginary loop. There is no actual loop, just an imaginary circular path. But everything else is same. So there is this magnetic field which is there. This magnetic field is changing. Magnetic field is changing. Because of that, obviously, there will be a flux change. 100%. Flux is also an imaginary concept. You cannot say flux has to be only through real objects. You can visualize an area through which you can consider some flux. Flux is always again imaginary. You can take how much flux is through this area, how much flux is through this area in air. You just measure the flux. There is no harm in that. And so that means again by Faraday's law, again by Faraday's law, again by Faraday's law, there must be EMF which is induced. There must be EMF which is induced. But then the real question comes. Till this point, everything was same. Yes, there is also potential difference. There is potential difference in that particular loop. But tell me one thing. Here, there was current in that conducting coil. Will there be current in this imaginary path? Answer it in the chat box quickly. Hi, Akshaya, welcome aboard. Yes, come on, my dear students. What do you think about it? Will there be current in that imaginary loop? Yes or no? Yes or no? Will there be imaginary current in that loop? Yes or no? Think carefully. No, right? How can there be current? Think about it logically. For current, you need charges. For current, you need charges. This is an imaginary thing in vacuum, in air. Where will the charges come? So, obviously, the only different part is there will be no current as there is no conductor. There is no conductor or charges or free charges. That's it. Oh, till this part, everything was there. So, are we then concluding that voltage was there, but current wasn't there? Potential difference was there, but current wasn't there? Yes. And what does voltage actually create? Think about it carefully. What does voltage, potential difference create? It creates electric field from high voltage to the low voltage. Now, if you use Lenz's law, it will become obvious that which direction will the current be. If let's say the flux was to be created in this direction, then the current will be in the clockwise direction, assuming the magnetic field was decreasing. So let's say magnetic field inside was becoming less intense. So to help it, you will produce a magnetic field inside. So the current induced will be in this direction, just to saying, using Lenz's law. So I can definitely then conclude over here, there is a missing step. Okay, there is a missing step over here, that there was electric field, there was electric field which was induced, because EMF is induced, so field is also induced, that forces the free charges, forces the free charges in the conductor in the conductor to produce the current by moving it. So the electric field was there, which was pushing it, which was applying the force, thereby the charges moved, and that's how current was created. But here, potential difference was there. There was induced electric field. There was induced electric induced electric field, but unfortunately there was nobody to push. It's like the teacher is there but the class bunked, so the teacher did not teach anyone. Simple fact. So field was there, force was not there because there was no charge, no current, no conductor. So this is the main thing what we are studying, induced electric field. This makes me conclude that changing magnetic fields produce what do they produce? Obviously changing flux, changing magnetic flux, thereby inducing electricity, induce EMF, thereby create potential difference, and thereby finally induces electric field. If a conductor is present, then induced current is produced. Else it is not produced. Induced electric field is produced. As simple as that. So, say for example, I take a certain region and I see that there is magnetic field which was there over here, which was very, very strong. Example, which was very, very strong. And let's say suddenly it becomes weak. So from this point to this scenario, the magnetic field has become weak. So the magnetic field becomes weak. What should happen? Induced magnetic field should be created inside. So to help it, to strengthen it, induced magnetic field should be created. And in which direction? Inside. So if you hold your thumb inside, the fingers will curl like this. So the EMF will be generated. Like this. So the EMF will be generated like this. And whichever direction the EMF is there, that's exactly the same direction where our electric field will be there. So induced electric field will be also in the same direction. Is this absolutely clear? I'm using Lenz's law over here. Yes, perfect. Hi, creative buddies. Welcome. Hi, great. I hope you enjoyed the class. HSEC, BJR. Hi, phone. Welcome. Now that you understood what is this concept of induced electric field, let me tell you one very interesting fact. When I spoke about this induced electric field, nowhere were there protons or electrons. That means these induced electric fields are not created by free charges, like protons or electrons, positive or negative charges. They are not created by it. This is very, very important. Rather, they are created by, rather, they are created by dB by dt. Magnetic field should change. That means this should not be zero. Rather, they are created by this particular thing. Whenever magnetic field changes, that is what is creating this kind of induced electric field. Usually our positive negative charges, for example, this is a positive charge, this will create electric field like this. No, this is not created by any kind of positive or negative charge. Rather, it is created because you moved a magnet. Just you take a magnet and you move it, magnetic field will change around your region. That will create electric field around you. How cool is that? That is what this explanation is. You just move a magnet in air here, just move it. It is creating, changing magnetic fields, that is inducing electric fields here. That is very cool. And now comes the interesting part. Sir, if positive or negative charge is not creating it, then where do these lines start from and where do they end at? That's the best answer that you can think of. Think, guys, it cannot come from positive, it cannot end at negative. So where will it come and where will it end? It cannot start, it cannot end. So it has to be closed loops. Yes, in fact, these electric field lines, you can see they form closed loops, which is very counterintuitive. So they are always going to be closed loops without any start or end. So they do not have any start or any end. They are just closed loops. Very cool fact. They are not going to start, they are not going to end, they are just going to be closed loops. So till now, we used to think if a field line is closed loop, it has to be magnetic, but nothing like that. A closed loop can be electric in nature if it is produced by changing magnetic field. If it is produced by changing magnetic field, it can still be a closed loop. Yeah, is that clear? Oh, Jiblika, I'm your student Kathir. All right, 2025 batch. I've joined IIT Madras. You helped me a lot in the journey. I'm so glad. Whoa, IIT Madras. Congratulations, Kathir. And you should not just put it in the live chat after the lecture. Put it up in the comments because many kids are going to watch these classes, and when they see our students cracking IITs, cracking JEE, and entering their dream colleges, they will be so proud of you. They will also be motivated and they will also work hard. And I always ask my students to come back and leave one comment. That's the only gift I want. I'm not asking you for any money or any some fancy gift or anything, treat, nothing. Just come and write one comment and one like. I will be very happy because other kids will get motivated truly by. Yeah. Great. Congratulations and enjoy your first year. It's going to be totally game changing because first year is always fun. Then you understand how the college life works and it will get more fun. But first year is always extra fun. Okay, so enjoy your IIT Madras life. All right. So, having said this, one more important thing which I want to talk about is this particular induced electric field which is there. Imagine if I had an electric field which starts from a positive charge and goes to a negative charge like this. Okay, so I have taken some diagram like this so that it feels like it has started from positive over here and it ended on a negative charge. Now, in such a scenario, imagine you start from this point, you go like this, and you come like this, and you again, let's say, come back over here. So imagine you go along a closed path. You go along a closed path. If you ask me what is the total work done in that closed path by that electric field, my answer will be here it will do positive work, zero work, negative work, zero work. So the total work will be zero. It makes sense because it is conservative in nature. Because it is conservative force, conservative force, conservative force in nature. So the work done in a closed path has to be zero. But now just take that scenario where you have induced fields. Induced fields don't have any start, they don't have any end. They themselves are closed loops. Keep that in mind. Okay, so our induced fields are closed loops. Now somebody decides to maybe start from a point here like this, goes like this, goes like this, goes like this, goes like this, and let's say comes here. What you will see is a very interesting thing. Here to here, positive work, maybe zero work, positive work. Okay, from here to here, some zero work. Here, not so much negative work, but some negative work, zero work, and again positive work. You will see that in this particular closed path, if you take the total work done, funny thing is it will not be zero. That means it will be non-conservative in nature. Non-conservative in nature. The amount of positive work and the amount of negative work will be completely different. You can take another convenient part, let's say like this. Just go along this. Every time positive work, and I'm back to the same place. Positive, 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 and back. So total work done is not zero. It will be positive number or some negative number if you go opposite. So it is definitely not going to be zero. That means it is non-conservative in nature. So this induced electric field is non-conservative field. It is non-conservative field in nature. That means the work in a closed path, work in a closed path, work done in a closed path is not zero. So it is a very important thing. It is a non-conservative field. Non-conservative field. So these are the most important properties that you should know. Is this absolutely clear? Yeah? Perfect. Sir, can I find out the value of this? Of course, yes, you can definitely find it out. It's not that difficult. So I'll tell you what you can do to find out this value in case it is asked. You, let's say, want to find out how much electric field is there over here. Just imagine you have to find how much is the value of this particular electric field. So just consider this particular part which is inside that electric field. I am interested in finding out how much is the value of this electric field. So use Faraday's law. So use Faraday's law, which says that my EMF magnitude wise is rate of change of flux, and flux is changing because of the field change. So it will be d into b into a by dt, out of which area is same, so it will come outside, and it will be nothing but dB by dt, of course. Now this EMF is exactly that potential difference. It is exactly that potential difference in that loop. Now if you remember, previously we have seen that if you go from one point to the other, which is separated by some distance dr, and let's say the potential difference changes by dV, potential difference, then the electric field which is there, magnitude wise is dV by dr. I'm just talking about the magnitude part of it, dV by dr. So think about it. I am interested in what is the voltage difference. That voltage difference will be field multiplied by the distance across which you are traveling. Now, when you take the EMF is in a coil. That means you're starting from one point and you're coming back to the same point. So this voltage, think about it, it will be nothing but the induced field, the induced induced field multiplied by the length of that particular loop. Voltage is field multiplied by distance. Voltage is E into the length. Now this length of that particular loop, whatever it is, you can take 2 pi r, or it's a square, whatever. So here it will be nothing but 2 pi r, as you can see. That is nothing but area of the loop, which is nothing but pi r square, okay, which will be pi r square multiplied by dB by dt. R will cancel, pi will cancel. So from this, we will get the induced field value, which will be pi has gone, 1 r has remained, of course, and this number 2 has come below, pi r has gone, and just left with dB by dt. So that will be the induced value of the field in this region. Okay, and I think, yeah, that r will also be there. It depends on that r. Is this absolutely clear, everyone? Yogendra, right now I am in Karnataka, but I was born in Tamil Nadu, did my education in Maharashtra. Yeah, okay, great, awesome. So now that we understood induced electric field, this is a very important concept, not from mains perspective, but from advanced perspective. So let's go to the final part, which is called as the eddy currents, which is called as the eddy currents. A very interesting concept. So imagine this. We have a conductor, random shape. Some disc is there, some lump of iron is there. Okay, it's some kind of conductor. And this conductor is in motion. This conductor is in motion. What will happen if this conductor is in motion in some magnetic field? In some magnetic field. Magnetic field is also there. Magnetic field is also there. Okay, what will happen because of that? Motional EMF will come. Yeah, motional EMF is going to come. So there will be small teeny mini batteries that you can think of. Just imagine some kind of battery here, right? Some kind of battery here. Everywhere there will be some small batteries which you can visualize. What will these batteries be connected to? Will they all be connected to something from outside? No, it's just a lump of mass which is moving inside a magnetic field. So it has no place to send that current. So what it will do? It will send the current within itself. So when it sends the current will choose the path of least resistance and it will complete its circuit like this. Maybe it will complete its circuit like this. And not just this, there will be many such conducting loops which will be formed over here like this. Due to motional EMF. Motional EMF is creating conducting current loops within the conductor, within our conductor. Now, is conductor's current in some nice direction? No, right? It is some random thing, depends on the nature of the material, least resistance path. So these loops are formed like circles, curves everywhere within that conductor. These current loops, they are only called as eddy current loops. They are called as eddy current loops. And this conducting current which is being produced, this only is called as the eddy current. This only is called as the eddy current. So what is eddy current? Eddy currents are those currents which are produced within the conductor, which follow the paths of least resistances within the conductor itself due to the motional EMF, meaning moving a conductor inside a magnetic field. So there are small current loops like that. Now, because of these currents, what will happen? Whenever current moves in a conductor, it produces energy loss, correct? So, whenever a current will go through any kind of loop, there will be some loop resistance there will be some loop resistance and that current will be going. So there will be some power loss, which will be current square multiplied by resistance. This is called as the eddy loss. This is called as the eddy loss. Eddy loss is because of the I squared R loss, which is in the current loops and the resistance of that conductor. Is it absolutely clear, everyone? Okay. Now, what happens because of this? There are many such phenomena which are attributed to eddy currents. Say, for example, I take a pendulum. And I am moving this pendulum left and right like this. And there is some magnetic field over here, or maybe I have brought a magnet close by. Okay, I take a magnet or something like this. The magnet is close by, so there is a magnetic field here. So because of which what will happen? Over here there will be eddy loss in the moving pendulum, because it's a conductor, it is moving, so eddy currents will be produced, so there will be eddy loss. So what will happen? The energy of oscillation will be eventually lost as heat, and the pendulum will stop, and the pendulum will eventually stop oscillating. So pendulum is moving, you bring a magnet, zwing, currents will start moving, and that's it. It will get hot. Yes, that pendulum will become hot and it will eventually stop. So where did that heat energy come from? From the currents. So where did it derive that current from? From the motion. So the kinetic energy got converted into heat. So the kinetic energy got converted into heat. Is that absolutely clear? The same principle is also used in the braking of high speed trains. So the wheels of the trains are metallic in nature, which are conductors. So you bring a magnet close to them, just like this. So the rotational kinetic energy will be converted into heat. The wheels will become hot, but they will lose it, and this happens even without touching it. Usually we think when you break a wheel, you are touching some rubber on that surface, so because of friction, it will stop. Here, there is no friction that you are encountering. It's just that, you're bringing a magnet close by, they are not even touching. The induced currents are creating those eddy losses, which loses the kinetic energy and converts into heat. So contactless braking. Even I can say the concept of induction heating also happens by this only, where you are converting some kind of kinetic energy, some kind of motional energy into the heat energy. All right, so these are some of the examples that you can think of eddy currents. Absolutely clear, everyone? Perfecto. Can we go ahead? Okay, awesome. Hi Sarah, welcome aboard, everyone. Great. Now that we understand what eddy currents and this power loss, everything is, imagine I give you a question, something like this, where we have a rail and there is some resistance over here. Okay. And there is a rod like this of certain length, and I give it some velocity, let's say V naught, and there is some magnetic field which is there everywhere. Magnetic field, and you give it that velocity and you leave it. Okay. Now there are two scenarios in this. Imagine you have to, first scenario, you have to maintain maintain the velocity. First scenario, you have to maintain the velocity. Second scenario, you push and leave it. You push that particular rod and you leave it. What will happen in both the scenarios? Why is there a difference? When you push and leave it, I think it will eventually stop because current will be produced, heat will be there, and that heat will cause that loss and it will eventually stop. So if you don't want it to stop, you have to maintain that velocity by pulling it. So first is how much is that force needed and how much power will be needed. That is the first one. And in the second scenario, question is how much heat will be generated till it stops. Till it stops. So till it stops, how much heat will be generated? That is the question. Okay, so let's solve both of them. In the first scenario, obviously when the rod moves, there is motional EMF, there is motional EMF. Simply put, it will be L into V into B. Okay, that velocity will be V naught. Okay, so L V naught into B. So because of that, there will be current which will be induced, which will be nothing but EMF by your resistance. EMF by your resistance. Therefore, that current will be L into V naught into B, the whole thing by resistance. Is that right? Everybody with me? Okay. Now comes the interesting part. This current which will be created, I think most likely it will be like this. This current will be like this. It will go like this, and like this. Will experience a force of ILB. This ILB force, because of a current carrying wire, will always experience ILB force. So that ILB force tries to decelerate the rod, but we have to maintain the velocity. So in order to maintain the velocity, an equal and opposite external force is needed. Equal and opposite external force is needed. So that force will be obviously IL into B, but I know I, so it will be L into V naught into B divided by R into LB. So therefore it will be V naught L square B square divided by R. So that is the force. That is the force. Everybody understood till this point how much force is needed? We can also find how much power will be needed. Power is force multiplied by velocity. So force is already known. So you multiply it by the velocity. So it will be nothing but V naught square L square B square divided by R will be the power which is required. This is one way of solving. But guess what? There is another way of solving without force. I'll tell you how. Till current, everything is same. So this was method 1. This was method 1 of solving this. Method number 2. What is that method number 2? What just happened? Yo. I'll just save this so that in case I lose this document, I should not be in a soup. My board has hanged for some reason. 1 second, guys. Okay, so what is method number 2? What is method number 2? The method 2 is, forget the forces, I'll just think logically. Whatever power will be required by me, whatever power I will need externally, that power will be lost in the resistance in I squared R. Think about it. Whatever that current is going to move, whatever that current is going to move in that resistor, that will cause I squared R losses. I squared R loss. That is what my external power will be. Isn't it, guys? So what is I? I already figured it out. So it will be L square V naught square B square divided by R square into R. So this will be L square V naught square B square divided by R. So that is my external power needed. Don't you see the answer is exactly the same? V square L square B square by R. Same thing here also, V square L square B square by R. Same thing. And you can also find the force even without ILB calculations, because power is nothing but force which you need multiplied by the velocity. So that will be equal to my L square V naught square B square divided by R. So V will cancel on both sides. So therefore, my external force will be L square B square V naught divided by R, which is exactly the same answer which I got. L square B square V naught divided by R. So whether you go via this method of power, which is via energy consideration, or you go via Newton's laws of force consideration, answer will be the same. And this technique you will see many times in motional EMF questions. Got it? The concept of eddy currents. This is exactly eddy currents if you notice, because this conductor is producing some current which is producing some loss. So either you solve via eddy loss or you solve via ILB Newton's laws, answer is the same. Going to the final explanation of this, you push and leave it, it will eventually stop. And the reason is there will be obviously some kind of a current which will be produced over here. Yes, current will be produced, and therefore that ILB force is going to decelerate it. So ILB force is going to decelerate it. But how do I figure it out? How much heat is produced? Because every time I will be different, speed will be different. Do I need to integrate it? Obviously not. Instead, think like this. By eddy losses, whatever heat is being generated, where is it exactly coming from? It is coming from the kinetic energy of that particular rod, isn't it? So what is the kinetic energy of the rod? It is half into mass of the rod into V naught square. That's it. That is the amount of heat generated. You don't have to do anything. That is the final answer. Isn't it fascinating? That's it. Crazy, isn't it? What a brilliant question. So that was your eddy currents, my dear warriors. And we have completed this particular section of EMI lecture number 2. Eddy currents, induced electric fields, and motional EMF along with rotating conductors and numerous problems. I hope you loved the session, enjoyed the class, liked the video, register for MVSAT, and also if you are not a part of the Sigma Express batch, be a part of it. Yes, the live classes are going to be taken for you in one shots, and whatever syllabus we can do in detail, we'll do it. Okay, this is your best opportunity. This was your Captain Shreyas signing off. Bye bye. Take care.